In this video, I want to find the cube roots of this number, I. And I want to find them in this form, a plus bi. Now, how am I going to do this? In order to do this properly, I need to rethink the way I see this number. Now, yes, it is just a letter, but if I were to rewrite it like this, I see it as a complex number. And I see it as split into reals and imaginary parts. Now, if we recall the polar form for complex numbers, for a complex number, which is z cosine theta plus I sine theta, then I know that I can manipulate any complex number in this form into the polar form if I have the real and imaginary parts of that complex number. So all we need to do, in fact, is find the modulus and the argument of this very complex number in order to put it in this form. Then, using the Morris Theorem, we're going to find the three cube roots. Now, when I draw my complex plane with the real and imaginary axis, the reals are 0, the imaginaries are 1. Let's say that this is 1. Then this here is the representation of this complex number in the complex plane. Now this is very nice because anyone can conclude that a line going from 0 to 1, its length is of course 1, and so our modulus is 1. And because this is a right angle, we know that a right angle is a 90 degrees angle or pi over 2 angle, and that is our argument. Hence, I can rewrite I as cosine of pi over 2 plus I sine pi over 2. Now that I have this, I can use the Morris theorem, which says that when you raise a complex number to some power, all you have to do to the polar form to make it equivalent is raise the modulus to that very same power. Let's say we're raising I to the power of a, then we need to raise z to the power of a, and we need to add the a here in front of the theta into cosine and into sine. And in effect, what we're doing here, we need to find the cube roots of I. So we're actually raising I to the power of 1 over 3. Just like when you need to find the square root of 2, you're actually raising 2 to the power of 1 over 2. And so I to the power of 1 over 3 is in fact going to be its modulus to the power of 1 over 3, and then this thing inside here with one notable difference, which is going to be the key to finding 3 cube roots, right? When we're asked to find cube roots, that means we need to find 3 of them, because if we're looking for cube roots, cube of course stands for 3, there are 3 roots. Quadratic equation has 2 roots. And you always have to remember that if you graph a function and you can't see, let's say it's a quadratic, and you can see that the function intersects the x-axis at 2 points, it means that the roots are imaginary. Now, I drifted off again. We're back to here. What we're going to do now is we're going to rewrite this as, right, 1 to the power of 1 over 3 is just 1. Then we have cosine, and something very important, pi over 2. To this we're going to add 2 pi k is some constant, and all of this over 3. Now what have I done here? This 2 pi simply represents us making a circle through the plane, right? So making a full, if you want to call it, clock, so going 1 hour further. That's what the 2 pi stands for. The k is just some constant, and we're going to be substituting some numbers into it. And the 3 comes from the fact that we're looking for 3 roots, and this we know because we need to find the cube roots. What we're going to do now is, can you even see this? Yes, you can. we need to pick 3 consecutive integers that we need to plug into k to get 3 roots. And while you can pick any consecutive integers, and by that I mean any, as in 454, 455, 456, it is markedly easier, and by far the easiest combination is this one, because you have a 0 which nicely eliminates this, you have a 1 occurring twice, the only change is the change in from plus to minus. That's my favorite combination. Now let's find the 3 roots. Case 1, where k is equal to minus 1. Don't forget that there is also a I sine of this same thing inside, right? Pi over 2 plus 2 pi k over 3. So, case 1, our first root is going to be cosine of pi over 2 plus 2 pi times minus 1 over 3 plus I sine pi over 2 plus 2 pi times minus 1 over 3. I will not be writing this all out in the next 2 roots, it's just too long. And I've made, this is my 3rd try at this problem. I've made a mistake every time I've tried this. So I'm trying to cut down on time. That's why I'm also, I don't sound as cheerful as I usually do. If I ever do. Now, let's isolate this for a moment. Can you see this? Yes. Pi over 2 minus 2 pi is equivalent to pi over 2 minus 4 pi over 2, which is of course minus 3 pi over 2. And when you divide minus 3 pi over 2 by 3, you get minus pi over 2. And so from this we find that the root that we're looking for is cosine of minus pi over 2 plus I sine of minus pi over 2. Right? These two are the same. So no matter which test you write or for which teacher you're trying to impress, you can just skip this step of trying to calculate the same thing again. I mean, it would just be very stupid of you to do this. Cosine of minus pi over 2, sine of minus pi over 2, these are obviously very easy. Or perhaps it's easier with cosine than with sine. If you just visualize your graphs, cosine of minus pi over 2 is of course 0, and if you think of sine of minus pi over 2, it's just minus 1. So the only thing that's left is minus 1 here, which means that our first root is minus I. Ta-da! Root number 1. I'll push this whole thing back a little bit, like this. We're now looking for root number 2. And root number 2 will be where k is 0. This is going to be markedly easier. I use the word markedly again. So cosine of pi over 2 over 3. It's just cosine of pi over 6 plus I sine pi over 6, right? Because this disappears. Or can you even see what I'm pointing at? This here, rather. The k disappears because it's 0. And from this, again, it shouldn't be difficult. You should know this. These are basic trigonometric identities. In case you don't, just imagine the pi as 180. And then we're dividing 180 by 6, which gives 30 degrees. And then we think back to our special triangles. Well, this is too small. Special triangles. Can you see this? Yes, you can. 30, 60, 90, and the sides are, the 3 goes next to 30, and the rest is just 1 and 2 with Pythagorean theorem. Cosine of 30 is adjacent over hypotenuse, square root of 3 over 2. Sine of 30 is opposite over hypotenuse, 1 over 2. And this is our root number 2. Square root of 3 over 2 plus a half I. That is our root number 2. Finally, we're looking for root number 3. I'm going to push this up a little bit more. root number 3 we're going to get by making k equal to 1. And so it's going to be pi over 2 plus 2 pi, which gives, in this case, it was minus 3 pi over 2. In this case, it's going to be, it's like 4 pi over 2, so it's 5 pi over 2, right? And so our last root, the third root, is going to be cosine of 5 pi over 2 plus y sine 5 pi over 2. Now this one is a little more difficult, simply because we have a 5, no, hang on, I forgot to divide by 3, 6. 5 pi over 6 and 5 pi over 6. I was going to say this one's going to be very difficult if we have to find the exact value of cosine of 5 pi over 2. 5 pi over 6, now it's a lot easier. All we actually have to do is look back up here and realize that cosine of 5 pi over 6 is, because of the properties of these trigonometric functions, we can find the value simply by looking at cosine of pi over 6. Because pi over 6 and minus 5 pi over 6 complement each other, don't they? Don't you think so? Do they even? Yeah, yes they do. So we have a cosine function. Pi over 6 is 30, we said, so that's here, 30. 5 pi over 6 is like 5 times 30, which is 150. This is a positive, and so the way that I like to work this out is say, okay, this is 30, this is 90, this is 180, hence the 50 has to be here, 150 has to be here. This is my, oh, you can't even see what I'm drawing. I'm so stupid. See? I'm tired. I've done a lot of videos today. 150 degrees is here. And now this 150 is 30 degrees away from the peak. Well, that, ladies and gentlemen, is exactly the same as this here. Because of the trigonometric properties. We're 30 degrees away from the peak here and here. The only difference is here we're in a negative quadrant and here we're in a positive quadrant. This means that we're going to take the same value of cosine of pi over 6 and make it negative, and that will then be equivalent to cosine of 5 pi over 6. Or if I talk in degrees rather than radians, cosine of 30 is going to be equal to negative cosine of 150 because of the trigonometric properties. Hence, we take the square root of 3 over 2 and we make it a negative, minus square root of 3 over 2. And the sine of pi over 6, let's draw the sine curve. Sine curve looks different. Perhaps I should draw this x, y. Sine of pi over 6 is here, 30 degrees, and the other one, which is 150, is going to be here, right? Yes, 150. Yes, and because I should have drawn it like this on the same line, because this is 30 degrees away from the x-intercept, and this is 30 degrees away from the x-intercept too. They lie on the same line, and if they lie on the same line, they are of the same value. Hence, sine of pi over 6 is equal to sine of 5 pi over 6. And so I can just copy this from up here to get I1 over 2. This is our third root, and we have written all of the roots in the required form. Here they are again. Can you see it? Yes, you can. This was quite a lengthy process. I've gone around all the trigonometric stuff, graphing and everything. It would be very useful for you to remember, to memorize cosine of 5 pi over 6, sine of 5 pi over 6. Most people like to find these values through the unit circle, which, and again you can't see what I'm doing, through the unit circle. I don't particularly like the unit circle. I find this method a lot easier. What you do is you simply orientate yourself, you change from radians into degrees, and you say, aha, we're at 150 degrees, and then pull yourself back and see the value where you're at. What does it equal in these small values? And then with the help of a nice special triangle, right? The other special triangle that you have to remember is 45 degrees, 45 degrees, 90 degrees, and that's 1 square root of 2. With the help of the special triangles, you can easily work out any angle anywhere where you want. And these are our 3 roots. We've used trigonometry, we've used de Morris theorem, complex plane, everything that you can think of. And I need a little bit of a break now. See you in the next video.